Okay, some of you guys went to the hackathon this past weekend. Congrats if you did that. That must have been a lot of fun. I was only there for a little bit of time, but I heard it was kind of fun. And I totally forgot to mention it, so sorry about that. But next semester, I think there's another one. I want to say there's another one in some point in the next semester. If not, then next year you can do the hackathon then too. Homework 4. You guys should have seen my inbox this morning. I recognize the fact that debugging is hard. Okay, I've said that probably 1,000 times during class here. I recognize that. And so I don't have too many more comments on that except to say that I know it's hard and you should do the best you can to get a working program. On the other side of the coin, there's also, correct me if I'm wrong, but many tough students tend to be perfectionists. Would that be a fair statement? Yeah. Yeah. Maggie's like, no, I'm not a perfectionist. Yeah. The thing about deadlines is sometimes you have to provide what you've got, even though it's not perfect. Okay, if you're passing like 99% of the tests or 90% of the tests, guess what? You're still going to get over a 90%, right? I mean, you just have to don't stress about, oh my gosh, it's 4 in the morning and I've been up all night finishing up this project. Now, provide what you have, go to bed, get ready for your next midterm, which is probably the next day, right? So anyway, those are my comments there. For the most part, very good job on this. Look, I don't mind if you guys really want to make it perfect. I'm just saying that trying to make it perfect for every assignment could make your eyes bleed a little bit in terms of getting staring at too much code too often. Okay. Any questions on homework 4? We're going to start to try to grade it probably tonight or tomorrow night, hopefully by the end of the week. The next assignment is on sorting, which is, I guess we're going to cover sorting on, I believe, this Wednesday. So I'll try to have the next project open up on Wednesday. This is another one. This is actually the first project where I'm going to give you free rein to do one part of the project. Like, all I'm going to say is you need to come up with a sorting algorithm of your own, or find one online that you can use for an algorithm and code it up or whatever. And there's actually 3 parts to it. I'll talk more about it later. But one of the parts is you could do whatever you want, which is kind of fun. Okay? Let's see, what else? We'll talk a little bit more about labs and things as we go along. Okay, any other questions before we go? Okay. So here's the schedule for today. First thing we're going to talk about is your public HTML folder. You guys all have one. Even if you didn't know you have one, you do. And we'll talk about that. Then we're going to talk about Lab 7, which is tonight's lab, which, guess what, uses your public HTML folder, which means it happens to do something with, it happens to be online, which will be kind of fun. And then we'll go into this other method for dealing with priority queues, which we talked about last week, called a heap. Not the heap. Like, have you ever heard of getting memory from the heap? Different structure altogether. This is an actual data structure. Okay? All right. And like the stack, right? Well, the stack is kind of a stack. Kind of is a stack. They're both regions of memory, but this is a different idea altogether. Okay, so what is this public HTML folder? If you go into your main folder on the homework server and do an ls, you will find that you have this folder called public_HTML, which stands for your own personal web space. Regardless of the fact that you may have never used it before, you actually have a Tufts CS web space, which you can get to by saying www.cs.tufts.edu/tilde your CS username. Woohoo, right? If you did that right now and don't have anything up, it'll probably just say can't find file or no file found or something like that. But what it is you get to put files there. In particular, if you put an index.html file in that location, and it is a proper HTML formatted file, actually, even if it was just a text file, it would probably be fine. But if it's a proper HTML file, it will actually read it, and there's your website, right? So if you already have a website, you can probably ignore this. But if you want another website or just want to play around with it, this is where it is. So that's kind of neat, right? It's actually really like your own for now. I don't think you should make a commercial site out of it or something. Tufts probably wouldn't be happy, but you can use it for what you want.
If you use it for commercial things.
If you use it for commercial things, Tufts will get live. Yeah.
Technically they could.
Yeah, Tufts would be upset at you if you were using it for commercial things. Alex.
Can you run scripts
You absolutely can. In fact, I'll talk about that in a second. But you can run scripts. You can run PHP scripts or Perl scripts or Python scripts or whatever. Or in fact, you can run a C++ script if you want. In fact, that's what we do in today's lab. OK, I'll show you. We have to go about it a special way. Actually, now that I think about it, you guys might only be allowed to run PHP and Perl. I think as a staff member or faculty member, I can write Python. But you might, and so we have to kind of do a little kludge to do it. But it works fine. You can see how we do it today. Yeah.
If we already have stuff there, is that a problem?
No, it's not a problem there unless you have a folder called Lab 7, which you probably don't. Yes.
Where is the public HTML folder in our, like, how do we get to
If it's right in your main folder, so you log on SSH in the first directory. There's a public HTML.
Desktop, not even
Nope, not even desktop. It's just right there. Yeah. Now, one thing you have to do is, if you are going to put an index.html file, you have to set it so that it's actually readable by everybody so that you can get to it from the World Wide Web. You do this with a program called chmod, right? Which stands for like change mode, which basically changes the file permissions on your file. And if you do chmod a plus r, that means all users can read, and then index.html, all users can read my index.html. You don't want to do that to files that you don't want people reading. Like your grade file is not set that way, right? It's set so you can't read it, as it turns out. And that's how you actually do that. So if you wanted to set up a little web page, that's where you can put it. Okay? All directories, if you want to have subfolders, your directories have to be both readable and what we call executable, which means you can. It's the way the web server deals with them. It has to be able to kind of see inside as an executable type. So you have to do that as well. Okay? And you can go back and look at this if you have other questions about it. Yeah.
Do we also have to do that for like executable, like a.out?
Yes, you do have to make the executable. Now, what I do in tonight's lab in tomorrow's lab for the make file, in the make file, I have this line right here, chmod a plus rx. I think it's try.html. So that will actually do it for you in the H file or in the make file. Charlie.
Can we use that same format with the a plus, but instead of using r and x, use the number codes?
You can use the number codes, yes, and it wouldn't be plus. It'd be just you use the number codes. Yeah, absolutely. It's just it's another way of specifying it. Okay, so the reason I'm bringing this all up is because A, it's kind of cool, and B, tonight's lab we actually use this, and you don't actually have to understand any of this to like run tonight's lab. You have to read the directions and like follow them. It's not that hard. But the one interesting thing is most of the time back-end languages aren't C++. Back-end being the programs on the server that get run from your web page. But tonight we're actually doing it with C++. And again, if you want to dig into the details, you can see how we've gone about letting you do that. It was a little tricky, but we did that. Okay. This is not a web programming class, so obviously I'm not going to make you do any web programming, but you certainly can take Comp 20 if you want to, or you can try to. It gets full really fast. If you're a CS major, you're in a much better position to take Comp 20. But there is a web-based design class here at Tufts, and probably at every other university in the world. Like everybody teaches it these days. Okay? Questions on that? On your public HTML or the fact that you actually have a website, which you may or may not know about. You've probably also got one by virtue of your Tufts username as well. I think that's another one that you can also use web space for. Yeah, yeah, Al?
Is there any rule against pointing like external domains that we like buy to these Tufts namespace?
Are there any? I don't think there's any problem with it. You may have you have to forward it basically correctly. And that it's not hard to do, but it's not like dead simple either. And you can't say run something from your web page here on the Tufts server that's being run on another server. Like the World Wide Web won't let you do that. It's a security issue. Yeah.
Do they delete our server space when we graduate?
Probably. They probably delete your server space when you graduate. Yeah. Yeah. Yeah.
Can you
1 second.
What the path name for this is again?
The path name.
Yeah, is
It-
it just Tilda? 'Cause I don't see it.
You don't see public underscore HTML in your regular tilde? OK, maybe it's got to be created. I don't think so, though. It should be there. Yeah. See me after class. We'll take a look. It should be there. Yeah. If it's not, then you might need to do something special for tonight's lab. But I don't know. Just do an ls in your tilde folder, in your regular folder. It's not there? All right. See me right after class. Nathan.
That was the same.
Same. You don't have one either?
No, I'm pretty sure I have it. I've LS a lot of times there.
You what?
I've LS a lot of times in that folder. I've never seen one.
Never seen a public HTML folder.
Yeah, I've
Okay, you can make one. Or, well, problem is you need to make it with the right permissions too. Well, I think the script will allow you to do that. But if it doesn't, I'm going to go to the first lab tonight and work out the details of that. Okay, other questions on that? All right. Okay, so last week I whet your appetite for these priority queues. Okay, remember what a priority queue was, right? Priority queue allows you to basically order things, although not really. You basically, behind the scenes, you've got some structure. And what you can do from the public interface is you can say, I can insert items into this based on a key and some element. The key is what we care about. That's the thing we're going to be ordering on. And then you can say, hey, what's the min element or the max element, right? Depending on the type of heap or type of priority queue you're using. And you can also do remove min. Okay, and that's about it. But the nice thing about that is, if you're trying to prioritize things, you can get stuff out in the priority that you put it in. Okay, based on the whole rest of the structure. We talked about the two different ways that we created a priority queue using a list. We had an unordered list, which was basically just the numbers in an array in no particular order. And we said, fine, doing an insert into an unordered list is easy. Stick it right at the end. Doing a min element, you have to go through every element. That's painful. It's order n. And the same thing with remove min. Kind of painful. Then we said, fine, let's keep our list ordered as we insert. And if we do that, then the insert takes order n for each element. And the min element actually is just order 1 because it's always the last one. So it's easy. You don't have to actually move anything. And remove min's the same way. Okay, so there were some trade-offs. All right, well, guess what? We can do better than this. You kind of knew we were going to do better than this, right? I mentioned it. There's another kind of data structure called a heap. Okay, in some sense, it's very similar to a binary heap. We'll see why in a minute. In another sense, it's very similar to like a heap of stuff where like the lightest element or something floats to the top or whatever. Actually, it's interesting. Yeah, what would this be under? Materials science or earth science or something? Have you ever taken you probably wouldn't have, like a bucket of sand or dirt or something, and if you shake it, what goes to the top? The little particles or the big ones? That's a good question. You should try it sometime. The big ones end up at the top. Okay, it's because the little ones basically fall through the cracks and end up kind of going under, and the big ones end up coming. This is why if you go buy a piece of property somewhere, and it's like hasn't been used for years, right? Or even if you're buying let's say you're buying a field to make like corn or something, right? You have to go and dig up, like till the field. A lot of times you end up with these big giant rocks in the middle of the field that are like kind of just under the surface. That's because they've been kind of slowly working their way up to the top of the surface. All the other dirt has been going under it. So the bigger things actually end up on the top. So a heap is kind of the same way, where whatever the most priority thing ends up on the top of this heap of stuff, and everything else is below it. And all you get access to is the top one. Okay? Going a little more specifically here, a heap is a tree-based structure. Okay, at least the way we think of it is a tree-based structure. You'll see why in a minute, what I mean when I say that. And it satisfies what we call the heap property. Okay, remember how the binary search tree followed the property that everything to the right or everything to the left is less than the element you're at, everything to the right is more, etc. The heap property is even simpler. Parents have a higher priority than their children. That's it. Okay, that is a heap. So this is what a heap looks like. Two types of heaps here. A min heap and a max heap. Okay, a min heap, in this case it starts with 5 at the root, and then the two children below it are 10 and 8. Does it matter which one's which? It actually doesn't matter at all in the case of the root here. Yeah. These are all keys, yes. So think of it this way, and we're going to talk strictly about the numbers, but think of it as dragging data along with it. So this is like your emergency room, right? The person who's got the priority 5 is like a person, and 5 is their priority. Yeah, that's all. Yeah. We'll get to all that. Yes, we'll get to inserting and removing, and in fact, you guys will try to figure some of that out in a minute. A max heap, on the other hand, just flips all the priorities. So all the priorities of the children are less than the priorities of the parent. Okay, that's the only difference between those two heaps. Yes.
Are they necessary binary trees, or can they
We're going to talk about a binary heap in this class. There are also other types of heaps that have more children than 2, but let's just stick to binary for now. If you want to go learn more about other types of heaps, that's cool. Okay? All right. Questions on this? The first time you see these, you go, wait a minute, that doesn't make any sense, because how do you know which direction to go and blah, 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 and all that? You don't, as it turns out. Okay? I mean, there's differences. This is not a binary search tree. It is just a binary tree that happens to have the heap property, which simply means that any children have to be, in this case for a min heap, have to be greater than their parent. Yeah?
Do you generally try to keep it AVL? These ones are really
That's a very good question. Do you try to keep it AVL? It turns out it doesn't matter. And you'll see why, the way we build this heap. Yeah, good question though. Nathan.
Essentially, it seems like if you could think of a binary tree where every time 2 branches are about to split, there's a device that gets spin around that area, a wheel that moves that part independently,
Uh-huh.
so that there's no order requirement, but it's still a binary tree.
Oh, I see. Yeah, okay, you can think of it that. Yeah, sure, you can think of it that way. What you do have to be careful of is that there are, what you have to be a little careful with is the children have to remain still, they still have to follow the heap property. But no, I see what you mean. There's no particular ordering between left and right. In a binary heap, there is no ordering between left and right. Good question. Okay? So this brings me right to my next slide here. This said there are no implied orderings. Unlike in a binary search tree, these are the same exact heaps, right? Well, not the same exact, but these are both heaps where you have 5 as the root, 10 is the left child, and 12 is the right, or 5 is the root, and 12 is the left, 10 is the right. They're both heaps. Why? Because the only heap property is the children have to be, in this case, greater than their parent. Yes?
Is it kind of like a stack in that the only thing you care about would be the top?
Yeah, well, it is kind of like a stack in that the only thing we're allowed to get out of the heap is the min element. Yep, and it's different than a stack, and there's no first in, first out sort of thing, but there's definitely, you're only allowed to touch the top one. So it's very similar to a queue or a stack in that sense. Charlie?
Are there any drawbacks or advantages to adding another invariant column, so making it a binary search tree as well as?
Yes, there are differences, right? Well, the first one is that you, if you're trying to find just the minimum element, this is a much better structure because it's order 1 to find the minimum element. Okay, where's the minimum element in this one? It's always the root, right? So there's your difference right there. Binary search tree, you have to actually search for the minimum. Go all the way left in that case, right? So there's a difference in that case. Better asymptotic complexity for minimum, which is good. Okay, now here it starts to get interesting. And this goes to exactly, you were asking, what's your name over there asking about the AVL? He's not looking at me. There you go. Name again, sorry? Morgan. Morgan? Yes. Morgan says, hey, do you have to make these AVL, right? And the answer is you don't have to, because the only way we can have a heap is if we make it a complete binary tree. Okay, in other words, you can't have anything going down here before you fill in left to right on the bottommost level. You're actually not even allowed in a heap structure. Okay? So what does that mean if it's a complete binary tree? Well, what's nice about that is the maximum amount of nodes are used. Yeah, basically you've got you're basically squishing the tree into the it probably should be minimum number of nodes. Internal nodes. Oh, sorry. Maximum number of nodes. Internal nodes are to the left of external nodes. Yeah, well, that's basically in the case of these are the external ones. They're all nulls. These are the internal nodes. Yes, question.
Where does this property come from?
Where does it?
Is it like a result of the heap property, or is it just like
Yeah.
something that we're all doing because it's nice?
Good question. We're doing it because it's nice.
Okay.
Yeah, it's not a part of the heap property. You're right. Right. It's not. We could make a heap certainly that has less. We could make a heap that doesn't look in this case, but in this case we're going to keep it complete binary tree. You'll see why in a few minutes. Okay. In fact, you're going to try to think about this for a second. What is the best way to actually store this heap? Okay. When I say store the heap, you know how to store binary search trees. You know how to store linked lists. You know how to store arrays and things. Let's think about the best way to store this heap. Here's what I want you to do. Talk to your neighbor, and if you don't understand the question, just think about it and go, what does he actually mean? In what form are we going to keep this heap? Is it just a binary search tree, and is that the best form? Like, in other words, is it best to have just a node and a left and a right? Okay, think about it for a sec. Talk to your neighbor. Think about it for a few minutes.
But why would that? But then what's the equilibrium? I'm trying to think about like why that's
Okay. All right, let's come back. You guys had a lot of good thinking, it sounded like. Who thinks they have a good idea for how to do a heap? No.
I was thinking that we could kind of link it to a queue in the sense like the values would be there.
Okay, a queue of some sort, okay.
So you can just easily access the elements, but like they would have different pointers.
So it's going to be a queue, but are you allowed to, it's an array of nodes. Okay, so you're allowed to, so it's not really a queue format. A queue would be, remember, queue comes in and out this way, right?
So it'd just be an array of nodes.
Ah, okay, an array. Okay, that's not a bad idea. Okay, I like it. Let's think a little bit more about that. Yeah, Logan?
I'm just kind of adding on to that array idea. Wouldn't it just be an array with twice the number of elements in the level up? So it'd be like every time you double the size of the array going down, and then you can just access it by like.
Okay, I like that. I like that. Does anybody think that it's just going to be just as simple to do a binary, like a search tree, like where you have a node and you have a left and a right like that, and you go down and then each one has a left and a right?
Because then you have to think about like how you're going to move stuff up and how you're going to
Yeah, you still have to do a little bit of that. You're right. And by the way, this is not a heap because it doesn't have the right. Okay. Yeah, that's a good. Francesca, you had a comment?
I was just going to say that if that was kind of my comment, is that if you use a binary search tree, then like how do you bring things back to the top after you take off?
Yeah, you do have to do something, and we'll actually figure that out. Yeah, Grant? Well, and this is a good question. By the way, that brings me to another kind of a good point. Is there a way to walk through a binary heap in order from like 5, then 8, then 10, then 11, then 12, then 13, then 14? Is there a way to do that? You can do that with a binary search tree, can't you? That would be the in-order traversal. There is no in-order traversal for a heap, so that's an interesting point. Level order, you could do level order, but that's not going to give you that's not going to be 5, 10, 8. If we wanted 5, 8, 10, you'd be in trouble there.
Because we said that order didn't matter.
Right, because we said that order didn't matter. Yeah, very good point. Yeah, good point. Yep.
So this would require a lot of math remembering to set up. But if you made like an array of linked lists, and
Okay.
and so each value of your array is the level starting at 0 that you're on in the tree.
Uh-huh.
So level 0
Oh.
has 2 to the 0 linked lists. Level 1 has 2 to the 1.
I think you're on the right track, except now you're making it like too advanced. But I think you're on the right track. I like what you're going to say. Alex, did you have another comment?
Oh, yeah, we were thinking that you could probably store it as like some sort of
Oh, okay.
Be very into tree territory.
That's kind of a tree. Yeah, it's kind of the same idea. But I like what you guys are thinking. Now, let's go back to what Manal was saying. Okay, let's come up with, let's say this was an array. Okay, let's try to figure out what the array was. Okay, let's see. How many elements do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, 11, 12, 13, 14, 15. So how long should we make this? And let's think about there's 15 total spots in that tree, not including all the null ones, right? Which is 15, which is really close to what number that we like in computer science? 16, which is 2 to the 4th, right? So let's try to make these like about the right array size for 2 to the 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. How did I count how did I miss by 1? Okay, so anyway, we'll do that. Let's just label this for a second. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, 16 total spots. Okay. Where should we put the 5? At 0? I hear 0, I hear 1, I hear 15. Anybody think in the middle? It's the middle of the tree. Yeah, okay, all right. Well, let's put it. We'll put it at 0 for right now. Why not? That was the first answer I heard. Okay, where should 10 go? 1. Okay. Where should 2 go? Or sorry, 8 go? 8, and then can I just keep going across? Like maybe 12, 11, 14, 13, 22, and 43, and all the rest are blank. It's actually not too bad, right? How do you find the parent, or sorry, how do you find the child of a node? If this is if 5 is at position 0, what are the children? How do we do this maybe mathematically? If we know the index, what could we do? What is it? So, 2n plus 1 and 2n plus 2, wouldn't that always give you the children? So let's look. So let's look at what are the children of 12? 22 and 43? 12 is here. 2n plus, so 2 times 3 is 6 plus 1 is 7, 22. 2n plus 2 would give you 8, which is 43. So look at this. We have now turned our binary tree into something very concrete in terms of an array. It is just an array. It's not even a queue. It's just an array. We just know that we're going to stick these elements in like this. Now, this is going to make the math easy. Now, for those of you who said 0, that's not a bad choice. For those of you who said 1, it's actually a better choice, as it turns out. So here's what I'm going to do. I'm going to actually do this. It's probably not quite as easy. But notice the formula we just had here, 2n plus 1 and 2n plus 2. It's slightly easier if we say this is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 10, 11, 12, 13, 14, 15, and we don't worry about that other one. And so I've just slid everybody else over by 1. Here's why. Let's go back to this. How is that going to change these two formulas? If 5 is at position 1, what are the 10 and 8 in terms of the position? 1 and 2, which would be, or sorry, 2 and 3, which would be 2n and 2n plus 1. Yeah, don't worry about the other direction. But for right now, I'm just going to tell you right now, the best way to do this is to leave position 0 empty, right? Because we did already add one extra spot, right? We added the spot up to 15. So there's actually, in this tree here, there's a total of 2n minus 1, but we gave it 2n spots. Just that minus 1 is just going to be the end here like this. It just makes the math a little bit easier. We didn't even go the other direction. How do you find the parent of a node? Let's say it's 14. What's 14's parent? 8. How do we find that if we know that 14 is at 6? Divide by 2. And it's actually a floor function, which means that you divide by 2 and forget about any extra decimals. So the parent of 14 is 6 divided by 2 is 3. It better be here. And then guess what? There's the parent. What about what's the other child of 8 is 13. 7 divided by 2 is what? 3. Right? From a floor perspective, we do 3, and it's also parent. Its parent is also 8. So we've actually got this is the left child. This is the right child. And the parent, right, is just n divided by 2, floor function like that. That's what those little bracket things mean. It means just divide by 2 and then go downwards until you get to an integer. That's that. Okay? So that's kind of cool. Now we've got a way to store these things. And is there any traversing necessary? No. No more traversing. All that linked baloney, forget it. You can have the entire heap right in this array. This is one of the reasons that we force it to be this complete heap, like a complete tree, because we want it to be able to fit into an array of a given size. So we know that if we add 1, 2, 3, 4, 5, 6 more nodes to this, the next node we're going to have to double the size of this structure. Because then we need how many 2n? 2 to the 5th is now 2 to the 5th is now 32, so we need to double the size. So it's kind of cool that way. Yeah, Charlie.
Can we turn it into a circular queue and just add a mod capacity?
No, don't do that. The reason, I mean, you're trying to make it too advanced. This is actually a very simple structure, as it turns out. It's actually even simpler than that. You don't need to worry about any mods or anything. Just stick it like this. Now, we have to talk about a couple other functions that we're going to need to do with this, which we have, because remember, it's a priority queue. But this is the best way to store it. You could store a binary search tree in this format, but the problem with the binary search tree is, remember, you can have a binary search tree that looks like this. Right? Every time you add another left here into another level, you have to double the size of your array. So unless you're keeping it very well balanced, then you need to you can do it this way. It's just not the most efficient. That's why a linked structure is better for a binary search tree. For a heap, because we know it's complete, we can always use the array. It's actually better. Yeah?
How is this viable for a large sensitive data?
How is it viable for large sensitive? That's a good question. I mean, remember, in a heap, you are inserting at the end. You're never going to get a non-complete heap, right? So in other words, it's always going to be maximally efficient in terms of the depth. So it's not too bad. I mean, it's no worse than a binary search tree in that sense. Yeah. Yeah. Good question. Yeah.
Do you have to worry about whether to add to the farthest right and farthest left paths?
Say again.
Do you have to worry about whether to add farthest right or farthest left paths?
You have to do furthest left first. Yep, you have to insert. We'll talk about inserting in a minute, but you have to make it so that it's always the next one that gets filled in this has to be the one to the left of 11. It has to be the next one that gets filled, whatever that means. And then guess what? We have to make it into a heap again if it's not. So this is what we just went over, the details of the positioning, right? We also have a heap size. The heap size is the number of elements that are actually in the heap, not including the null nodes or the ones that are empty. Okay, all the other ones are the ones that matter. Like that's when you say heap size. Okay, and there's the equations. So all these, it's a very fast structure as well. Yes.
So that 0 one,
Yeah.
one right there, we're basically wasting memory.
We're wasting one little part of the thing. Yes. Yep, we're wasting that. Now, many times, some people who actually implement this will use that for a swap place. So they'll say, I'm not going to waste it. I'm going to use it. Because if I ever have to swap two things, put this one here, put that one there, put that one there. You see what I mean? So it actually gets used. It's kind of beautiful, yeah, in that case. Somebody had a question over here. No, OK. All right, yeah.
Since you're wasting the 0, do you not have to increase the...
We do, but remember, this binary tree has how many nodes in it, including all the null ones?
Right.
2 to the n minus 1. So there's the minus 1. We just put it at the beginning, and it just makes the math just a little easier. You could have done the math without it, but it just makes it easier. Floor gets a little fuzzy otherwise. Or not floor, the child-parent relationship. But this is the easiest way. OK. All right. Remember our priority queue operations. OK, we're going to sometimes just call them heap operations because they're the same operations. Priority queue is the abstract data type. The heap is now the data structure we're going to use. OK? And in this case, the heap ones that we care about are min element for a min heap. Okay, insert item and remove min, same as before. Okay, and we could change that with max element if it was a max heap. Okay. All right. How are we going to do min element? What's at 1? Isn't that easy? Look at this heap. 5 is the min element, and where is it always going to be located? Right there. Okay, so if we have this array, I'll just call it heap. I don't know, heap at 1 is our min element. Okay, boy, that's easy. What's the asymptotic complexity of that? Constant. Woohoo! So for our first one, we got constant. Okay, there it is. Return the heap of 1. And that's it. Okay, now I want you guys to think about how insert might work. Now, here's the setup. For insert, we're going to somehow insert 9 in here, in this binary heap. And I want you to think about this. How we're going to insert 9, where we're going to insert, and then what we're going to do once we insert it to keep it holding the heap property. Okay, so think about that. Take 5 or 6 minutes to think about that. Talk amongst yourselves. Okay. Guys have any ideas? What are you thinking?
Idealistically, what should we end up with?
Yeah, it's a good question. What do you end up with a heap, right? You need to just end up with another heap.
So it's like that should be where 10 is.
Yeah.
And then 10 should go down, and 10 is smaller than the number.
Yeah. So, okay. So where could you put 9 to begin with? How about this? Where's the next open spot? Yeah, index at 10. Perfect. And if it's index at 10, then you need to do what? It's wrong. It's not a heap right now, right? What do you need? 9 needs to go up the heap, right? Okay, so if 9 goes up the heap, what do we compare it to? It's the only thing we can really compare it to. Okay, so what's the first thing it knows about? 9's comparing. No, 9 doesn't. 9 has no real way to get to 5. Okay, it could compare to 5, sure. But what's its parent? Can we figure out its parent using a really quick operation? Divide by 2, right? So let's see. If we divide 10 by 2, we get 5. So what's at 5? 11. So compare it. Do they have to swap? Let's swap them. And then what do you do? Okay, and then so 9 is now where 11 was, so 9 is going to get paired to 10. Good. Right, good. And then does it need to swap? So swap them. And then what? Compare it to 5, and then what? No swap, you're done. Ooh, is this now a heap?
But 11, wouldn't 11 need to be swapped with 14?
No. Think about the heap property. It's not a binary search tree. Heap, right? Yeah. Good. All right. I know I heard a lot of really good thinking here. Now, those guys over there I just talked to, they're not allowed to answer. But who has some ideas? What do you guys think of ideas-wise? I want to see more hands than that. I'm going to make you talk for more time. Yes?
We were thinking find the row that it would fit in.
Find the row. Oh, find the row that would fit in. I'm not sure you're always going to be able to do that. Right? Because, I mean, what do you mean it's got to be less than that row? Or like, it could fit on 2 rows depending on how you define that. And then that's the other thing is, do you really want to think about this in terms of rows? I think we want to think about it in terms of left child and right child or parents, not in terms of rows. Good idea. I'm curious how that would pan out. But let's say you figured out where. So where would 9 go in this case?
So we were saying replace 10 with 9.
Place 10 with 9, okay.
And then find the max of the third row and replace that with 10.
Find the max of third row. Okay, what would the asymptotic complexity of that be? I think it would be linear, right? We're trying to avoid linear if we can help it. But that's you would have to basically go through the whole thing, and then it would get a little weird trying to go linear, like level order. But interesting idea. Francesco, what do you think?
Can't you replace 10 with 9 and then move the left child of 10 and the left child of 12 down and shift it over?
You can't move them down because you have to fill these guys first.
What's I'm saying? So 10 gets 9.
Okay, 10 gets 9. How did you find 10, first of all?
Checking to see if the key is greater than 5 and then greater than the left and right child of 5.
But it could be either. Right? What if it was 5, 7, 8, and we were trying to insert 9? Then would you go to the next level? Is that what you'd do? I guess so. I think that's okay. That's an idea. I'm just trying to think of practically how we're gonna still have to pretty much go through the whole tree, though, don't we? And doing it level order is even trickier. Good idea. Good idea. Yeah.
Sort of on the same line, are we trying to fill in the left child of 11 next?
Yes, we have to make when we add 9, the rest of the heap will finally end up where there's something's going to be here and everybody else is going to be there. You can't add it anywhere else.
So basically, wouldn't the best strategy to sort of be able to find that next slot?
Okay, and by the way, we know the size. We know the size, right? And we know the size in this case is 7, right? 1, 2, 3, 4, 5, 6, 8. We know this, so we can put it there, right? Okay, yeah, all right. So what's your idea?
And then you would move 11 down and 10 down.
Oh, that's not a bad idea at all. So basically, put it in the next spot available. Kind of like that, because that's definitely one that has to be filled. Okay, 2 more comments. Yeah, Logan.
What if you started at the back? So like element 10 in this way.
That's just what he was just saying. Yep.
That's right. And then you divide by 2.
Yeah.
And then you check when you check.
Ah.
And if it's
Yeah.
bigger or less, then you.
That's exactly what he was saying, except doing. He was saying it via the diagram. That you're saying it how to do in the array. I like that. That's very good.
And that's exactly what I was.
And that's what you're going to say too. Okay. So I think what we've got here is where are we going to put 9 to begin with? Logan, you said it.
We have to put it in element 10.
Okay. So 9 goes in the next available place. If we put 9 here, is it a heap? Why? Because the 9 needs to be like greater than its parent, right? Okay, is there an easy way to check, and Logan actually said, is there an easy way to check who's 9, compare against 9's parent? How do you do that? You check 10, you divide the index by 2, and that gives you the parent, and you say who's bigger, 9 or 11? And if the answer is the one that's like the one we just added, then you swap these two. And this might be a place where if you wanted to use that other location, you could, right? Okay, 9 there and 11 there. Would it now be a heap? And I'm sorry I'm not drawing all this, but would it now be a heap? No, because it would go 5, 10, 9, 11. What do you have to do then? Divide by 2. So now it's at 5. 5 divided by 2 is 2 in integer math. So compare it to is not 9 versus 10. That is 9's parent. Which, do they get swapped or do they stay? Swapped. So 9 and 10 get swapped. So it's going to be 9 and 10. And then we have to do it at least one more time, right? Well, one more time. 2 divided by 2 is 1. Compare 9 and 5. Do they need to be swapped? No, that's exactly right. So I will go through the exact algorithm in a second.
Would we use this recursively to function that?
Would you use it recursively? A while loop's probably easier in this case. Yeah, a while loop's pretty easy in this case because you know how many you have to do, or even a for loop. I mean, you know how many times you have to go up, right? Basically, can just divide. Well, let's see. A while loop would probably work. Yeah, because you're just basically dividing by 2 until you get to 0. Then you're done. Yeah, good question. Yep.
So this works because the only rule is that the parent has a higher.
Yeah, a higher priority, or in this case, a lower number.
So
Yeah.
it doesn't matter that 14 is above 11.
Does not matter. Well, okay, hold on. Yeah. It doesn't matter that 14 is above 11 in the sense of its children, because 14's children, right now they're undefined, but they will never be, the children will never be less. But the level can go as far down as you want as far as level goes, sure. Yep, very good point. Alex, you had a comment?
Yeah, I'm kind of lost.
Okay, I tell you what, let me go through the algorithm on the next slide, and then you'll see if you're still lost.
Yeah.
Good question, or good comment. Yep.
Wouldn't we only have to go until we find a true statement where like the one we're switching is less than?
Yeah, you only have to go until you do not have to swap. Yep, very good point. So that's where another place for a while. So Senator, to answer your question, you probably could do this recursively. I just don't think it's necessary in this case. Yeah. Okay, here's the algorithm. Alex, you ready for this? Here's the algorithm. Insert the element at heap size plus 1. Okay? So heap size was, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. Oh, we were wrong. Heap size is 9, wasn't it? Thank you. Heap size was 9. Insert at 9 plus 1. Okay, that's what we did. We put the 9 right here. Okay, and then we have this term called a bubble up or an up heap. And that's what you guys were doing in your brains, right? You were saying you were moving that element up the heap until it couldn't go any farther. How do you do the up heap? Compare the element with its parent. Easy, divide by 2 to find its parent. The index, divide by 2. If it's in the correct order, you're done. That's what Moretta was saying. If it's not in the order, swap the 2 and repeat step 2. There's your algorithm. Okay. Now, Alex, for instance.
How are we able to tell what parent, which element in this array is the parent? Oh.
Divide by 2. And take the floor. It's easy. Right? Yes?
What if it's the right child?
If it's well, this is the parent, not this is the parent. So, okay, so if it was 9, 10 divided by 2 is
I mean, what if
5. Let's do 9. So the parents of, let me go back one. The parents of 12, or the children of 10 are 12 and 11, right? Okay, of course I switched it already. Let me do it at 14. Let's do the parents of 8. I didn't switch this side at all. Okay, the children of 8 rather. The children of 8 are 14 and 13. Okay, so if you go to, here's where they are. What is 6 divided by 2?
3.
What is 7 divided by 2?
3.5.
It's just 3. You do integer division.
Oh.
So 7 and 6 both have a parent at 3. Make sense?
Okay.
Okay. Yeah.
So I think someone already asked this question, but so the final, when you insert 9 here, it's 5, 9, 10, 11.
5, 9, 10, 11.
Right, so it's okay that 11 is under 14?
Yeah, this is exactly the same. Yeah, same question. It doesn't matter. This side, who cares? It's whatever as long as 5 is less than 10, which is less, or 5 is less than 9, which is less than 10, which is less than 11, then it's a heap. Yep, you're absolutely right. Okay, you don't need to worry about side to side in that case. Okay. All right, so we've got the algorithm, and now we know how to do it. If you want, you can certainly go to the visualization here. Same website I've been to before, and it actually shows you, right? So if we were to insert, let's insert 10 into here, okay? And let's insert, actually, let's do this. Let me go back and make it exactly what it was, just so you can see what's going on. Let's do this. I will increase this. Let's see. I thought I could move controls. There we go. Okay, so insert 5, insert 9, insert 8, insert No, it wasn't 9, was it? We wanted the original. Shoot, hang on. Yeah, let me do it again. There we go. Insert 5, and then 10, and then 8, and then 12, and then 11, and then 14. I'll move the screen down in a minute, and then 13, and then 22, and then 43, and that was it, right? That was where we started with. Like that. Okay, so that's the heap we started with. Now I'll slow it down a little bit, and I'll slow it down a lot. And we're going to insert 9. 9 is going to go down here. It's the next available spot underneath. It's the left child of 11. Okay, so 9 goes in right there. And we will put it there, compare, swap, compare, swap, compare with 5, no need to swap. That's all. That's an up heap. Okay? That is defined as an up heap. Okay? All right. Questions on that? You want to do another one? Want to insert something else here? What else should we insert? 3. Okay, where's 3 going to go? No, 3's, well, it's going to end up at the very top. But you're going to put it underneath the 10 because it's the next available spot. And then you're going to check 3 with 10, check 3 with 9, swap, check 3 with 5, swap, and 3 is going to appear. And it's going to go 3, 5, 9, 10. At least that's what it should be, right? I'm going to speed it up just a little bit. Insert 3, and there we go. Okay, swap, 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 and we're done. Okay. What if we inserted 107? 107 would go into the position right under 14 and check, and we are done. Ben?
Is there a position where something gets swapped up top and has to be compared with its right child?
What, can you think of a time? If it gets swapped up to top, we already know that both children are already greater than this one. So there's no way it could get to the top and then have to go the other way and do it. Yeah?
So what if you insert something else with the other child of 14 as well, and then you try to insert 14?
If you insert child of 14 and 14 is already in the
No, it's
heap,
like, let's say you do like 72 or something.
let's do 72. 72, and then what?
And then you do 14. Would that just go under 13?
Because 14 is already in the.
But what if you want to do another?
I don't know how. I think it either guesses, like it just puts it in either, or it doesn't matter. So it doesn't actually. So is it true that 14 is still? Is it still a heap? Sure. Now we've got dual elements in there, but that's okay.
So like if you want to do the thing where you just have a counter that keeps track of how many of each number you have, like.
Yeah, you probably won't do that in this one.
Okay.
Yeah, you probably won't do that in this one. You'll probably just add it, and then you just make a choice of whether it's bigger or small. I mean, the bigger or smaller, you just put it. Doesn't matter really in this case. Yeah. Yeah.
Is this still a valid heap because the 13 has the 14 as a child?
Well, yeah. So every parent, there's no place where a parent is greater than its child.
Okay.
Right? And that's the definition of the heap. Yeah.
So in terms of run size, is this going to take somewhere between like 1 and heap size?
In terms of asymptotic complexity? Yeah, let's think about the asymptotic complexity for a second. Putting it here, do you have to look at anything that way of it? You only have to go up the tree, which means it's going to be what? Logarithmic, right? You're going to go here, 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 and up the tree. You only have to go the height of the tree. Because it's already a complete binary tree, logarithmic is always going to be the case. In fact, it's never going to be worse, which is even better than like binary trees. Right? Yeah. Yeah.
I'm just a little confused about why it's useful to have.
Let me back this up. Yeah.
Yeah, like what I was asking before, like it seems weird that it's out of order like that, even though that it satisfies the condition of the parent, so it's
Yep.
lower, I guess in this case.
Sure.
It's a child. Like, why is that useful if you have like a 107 right there? Like
Yeah.
a 9?
Remember what we're trying to do. All we care about is which element in that right there. That's the only one I care about in this whole heap. The 3, right? I don't care what's below it, right? But, and we'll get to what happens when you remove 3 about what happens as far as changing the heap. It actually works out just fine, as it turns out. Yeah, so you'll see when we get to the remove, which is in a second. Yeah,
There's
Retta.
still the 2 14s in there. And then
Okay.
You go about removing, so eventually one of the 14s is going to be your root.
Sure.
You remove until you get to the root.
Sure.
After you remove it, you you're still gonna have your smallest being equals what? what's
Sure.
the smallest?
Yeah.
Okay.
Well, yeah, because you've got 2 in there. I mean, that's the only, it's just because you have 2. But yes, you're right. Still equal to the smallest is still the 14, if the 14 was there.
I
Yeah.
mean, this question about the two 14s is a very realistic question, considering one of the key properties of priority queues is that you can't have 2 queues that are equal.
No, you can actually. You are allowed to. It just means that you can't differentiate between the 2 as far as priority goes. So you have no way of, right. If you say you and I have the same exact priority, and then we go into this heap, and then one of us comes out first and the other is second, whichever happens to come out based on the underlying thing.
That are numerically.
Yeah, exactly.
put equal.
Exactly. Yeah, Nathan? And then,
Well, you could also do it, I'm not sure if it's possible to overload the less than or greater than operators on
oh,
classes.
it is.
In which case, you could create a node class with a number and a count, sort of like the one we
Oh, I see. You could have a count.
the less than greater than and have an array of those.
Well, yeah, I suppose you could. The problem with having a count in this case is that you could be on the wrong side of the tree and you don't know where that 14 is, right? So that's the problem. If 14 happened to be on the left-hand side of the tree and we're inserting the right-hand side of the tree, we'd never find the 14 in order to make it a count of 2. So there's the issue with that. We can't duplicate using this count method anymore. But as it turns out, it doesn't even matter really. I mean, it matters if you really care about the priority of 2 similar elements. But then in that case, make them different priorities. I mean, that's the bottom line there. Yes?
Let's say you do remove until 14 is the root.
Okay.
At that point, either 14 is the root of the other 14, or
Sure.
14 is a child of a
Sure,
child
sure,
of 14.
sure, sure.
Then
Yeah.
your heap property seems to.
No, the heap property would be the same. Right? The heap property would still be the same. It would still be, when you do the remove, you'll see what happens when remove. You do the remove, it'll work out.
The parent isn't greater than the child.
It'll be equal to it. Yeah, that's fine.
Or it's.
That's fine. Greater than or equal is fine too.
Okay.
In this case, that's fine. Yeah, good question. Good question though. Okay, all right, let me go back here. And what I'm going to have you guys think about next, we did the insert, swap, 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 done. Okay, log n. Okay, the worst case, average case, turns out it's constant. Now, am I going to show you what this? No, there's a paper. If you want to read the paper, there's this paper here, which you can get if you happen to be on campus or a member of the IEEE, which we talked about the other day. And you can read it, and it will tell you about the average complexity of a heap. And it turns out that remove, even though it looks like the worst case log n, average complexity turns out is constant, which is awesome. Yes?
I was just about to think, how is that possible? But then I remembered there's no traversing in order to insert. You're doing it at the end.
You're doing it at the end, yeah.
As long as you don't have to swap, it will be constant.
As long as you don't have a swap, it'll be literally constant. Even if you have a swap or 2, it's still, on average, constant. Yeah. So anyway, take a look at that. Now, remove min. Which one needs to go away if we're removing it? The 5. OK. Using that information, try to figure out what has to happen next. I want you to 5 minutes. Talk amongst yourselves about removing the minimum.
Can we move it up just so we can see the array stuff?
Yeah, I'll move it up. And then let me make the array back to what it was. I don't think this is it. 5, 9, 8, 12, 10, 14, 11. Could you use recursion here? I suppose you could. Again, I don't know that it's necessary.
We can just like for each level, just do at that level.
Yeah, you probably could. Yeah. What's your idea so far?
Just take the minimum from the
But take the root.
down. So
Oh, take the minimum from the next level down.
5, take 8, and then take 10, and then take 13.
So you have to. What's the asymptotic complexity?
Log n probably.
It looks to me like you're taking the minimum of every level, which means you're going to have to go through all the nodes.
You bubble down.
What are you bubbling down?
Like start as over and like swap it going down. I guess though.
Swap with. How do you know to swap?
Oh, that's right. You don't know how to find the child.
Well, you do. You know how to find the child, but how do you know to swap? How do you know the difference between 9 and 8? Guess you could compare them. Pick one random, but then you've got to. If you pick one at random, then you don't necessarily know that it's going to be right. Because in this case, you can't put 9 above 8, but you can put 8 above 9. So you'd have to pick the correct ones. That means again, you'd have to go through the whole tree. So that's linear, which is not what you want.
I mean, the next thing. Whatever. When is this registration for you?
What's that?
When is class registration for
Next week.
Next week?
I think so. Yeah, I know. Getting there. What are you guys thinking?
Okay, originally we thought we could just like move 13 up and then 10 up and 9 up, but then like we realized that that doesn't keep the order because like 9 is greater than 8.
Yeah, that would be bad.
We inserted something by breaking the heap property at the end of the array. So would we remove something by breaking the heap property at the beginning of the array?
I like that. That's a very good idea. So what are you going to do?
So we'd move the, I guess,
You're kind of doing both, actually.
the root to like the very end of the array, right?
Well, we're getting rid of the root.
We'd move the thing at the end of the array to the beginning.
And then what?
And then once we had the thing at the beginning, we could then find its children and...
I like that. I like that idea. Okay, I think I heard some very good ideas here. Very good ideas. Who thinks they have a good one? I know Alex has a good one, but I'm going to let him wait because I think he has a too good a one right now. Morgan.
So sort of like what we were doing last time, you had to like add the last element. This time you have to remove the last element.
Okay.
So take 13 and so like remove 5 and take 13 and put it where 5 was.
Oh, I like that.
And then bubble up anything below that needs to get bubbled up.
So basically, 5 is going to get returned or deleted or whatever. Morgan says, you know that this is going to end up empty at the end of this because we're removing an element. So this one's gone. So you might as well get rid of it now. Put it here. Now, you're saying bubble up.
Or bubble down.
Ah, now that is what I like, okay? Bubble down. If this is 13 up here, okay, which one has to be here next to keep our heap property? The 8. Yeah, good. So we're going to have to swap that one. Nathan, question.
Essentially, you would take that 13.
Yep, 13 here.
You could just swap it with the lower of the two children nodes.
There you go.
Down until you don't have to do that.
That's called a bubble down. You have to swap it with the smaller of the two children. And the 13 ends up going here. 8 goes here. Does 13 versus 14 and 11, does one of them need to swap? Or I mean, it has to swap with a smaller one, right? It's the smaller of the two children that happens to be smaller than this one. 13 would go here. I'm going to walk us through this too, but that's exactly right. So we've got two ideas here, a bubble up and a bubble down. Okay, so here you go. Here's the algorithm. We are removing the root, and we need to retain a complete tree. Replace the root with the last element. Check. Okay, we remove the last element. Bubble down or down heap the root by comparing the root with its children. If they're both children happen to be greater, we're doing a max heap. If both children happen to be greater, stop. Right? If the children, if not, swap with the smallest child. Right? And you have to be careful. And this is for the lab next week when we do a heap lab. be careful that you remember to check if the children actually exist, right? If the right child exists, you know the left one has to exist, because otherwise it couldn't be a heap. But if the left child exists, you don't know that the, if the right child exists, you don't know that the left exists. Did I say that wrong? If the right, no, if the left exists, if the right exists, the left must. Right, if the left exists, it might exist. It might not. So yeah, Ben?
Well, actually, never mind.
Okay, but anyway, this is it. Let me walk you through this one. We're going to remove the minimum here from the 5. So the 5 goes away, right? Which one to replace it with? The next one that's going to be null this time, might as well take the 13. Some people thought, oh, let's do it with this one or this one, but you don't really know which. The one you know that, as long as you do it through the last one, you know that you can bubble it down all the way. Right? Otherwise, you're going to be in trouble because you don't know otherwise. Everything else is still in place. So we swap it with, we put the 13 at the root, and then we start swapping. And we say, OK, fine, it's got to be the swap with the smaller child because it's definitely greater than both children. Again, this one doesn't happen to be greater than both children, but it's greater than one of the children. Swap with it, and you're done. OK? Asymptotic complexity? Logarithmic. Not necessarily always. Could be. It's pretty close, though, yeah.
In the best case, you'll still have to do some bubbling.
You'll still have to do some bubbling, and in general, you have to do some bubbling down, yes. Yeah. Yeah, in the worst case, you have to do all the bubbling. So this is definitely logarithmic. But it's better than the n we had for the other lists and things, yeah, for the other ones we had. OK, so now we've got this. So let's go back just to remind ourselves. What was it? Not remove min, but it was just the min. Min element is what? What was the logarithmic complexity min element? Constant. Just boop. In this case, it's 8. OK. Remove min, or insert min. What was the logarithmic complexity? It was constant, but you could call it log n, and I would not take any points off. It's the worst case is log n. Yep. And then for the remove, we said it's log n. Okay, better than both of the 2 lists we tried before. Not bad. A couple more comments on this. Comment number 1. How easy, given a heap, is it to sort the elements? If you just wanted if you wanted this sorted, what would you do? Al? Remove min over and over, all right? Remove min, remove min, remove min, remove min, remove min, and you get them in right in order. Okay, you do destroy the heap that way, right? But it would be fast, yeah. So this is actually a pretty good sorting method called a heap sort, as it turns out. We'll get into that next week. Okay, and that's that. Okay, question.
Is heap sort like fast? Like I had a teacher in high school who yelled at me that heap sort was not as fast as quick sort. Is that right?
It depends. We will talk all about sorting on Wednesday and next Monday. But yeah, and your next project's going to be on sorting. But we'll talk about which sorts are, quote, faster than the others. Charlie and then Nathan. Yeah.
Isn't that linear complexity though? Or
Isn't it linear complexity? Sure. But you can't do better than that in, yeah. You actually have to, we'll talk about the inserting. We'll talk about one other thing in a second that we'll get to. But yeah, that would be linear because you would have to do, it'd actually be linear, it'd be not linear, it'd be n log n, because for each one, right, it'd be n log n, which is the best you can do for, in general terms, for a sort. Nathan? Yeah.
One thing you could do is just create an extra copy of the heap and sort that thing so you still have a heap.
Sure. You could create an extra copy and do that. Yep, absolutely.
Like I did for finding of a certain position on a queue.
Uh,
For students, you could create a copy of the queue and then just count the queues and then.
Right, you could create a copy of the queue. Right, exactly. You could do that. Yeah, you would just have another copy of the queue. Sure. There's other methods for that, but yes, good point. Yeah. Sure. There are lots of different sorts you could do on this, but the heap sort happens to be easiest on this one. Yeah, because it's already it already is in the heap property in the array. So don't go doing another sort if you already know. Taking advantage of the fact that it's heap property.
And they'll come out to the same thing.
Yes, exactly. Yeah. So here's another question for you. What's the best method for building a heap from scratch? Well, one easy method, but what's the best one is the question. Yeah.
sorting first?
No, you don't want to sort first. That would take forever. I mean, you don't want to go and sort things first if you don't have to. The easiest way, which you could do already, was just to do what?
Just do a whole bunch of
just do a whole bunch of inserts, right? You'd insert 14, and then you'd insert 9 and potentially bubble up, and then insert 13 and potentially bubble up, et cetera, et cetera. So that's one way to do that, right? That would take, each insertion takes log n, and we have to insert n. So this, just to insert into a heap this way, would take n log n, because you're going through all the elements, and each one is a logarithmic behavior, right? Although we kind of already said that insert is constant on average, so it's not too bad. Still more or less logarithmic. But there's a really cool way, which I wouldn't, if we had maybe 10 more minutes, I'd ask you to maybe think about. But this one, I would not have thought of this. OK, ready for this? There's a better way. All right. First things first. Throw all the elements into the array, right? Into a binary tree. Yeah, into the array or into the binary tree in whatever order they're in. OK, so just throw them in there. Then, this is cool. You start with the lowest completely filled level at the first node with children. I'll show you what that means in a second. All right? Happens to be at position n divided by 2. Right? And I'll show you why in a sec. And then you downheap each element, and you actually do it faster. So this is what it looks like. OK? All right. So we have, and I'm going to walk through this whole thing here. OK. We just threw these elements in the array. Is this the heap property for a min heap? No, not at all. OK, because we just chucked them in there, and we're doing that. But now, the first node, OK, if we know the number of nodes, in this case it's what? 1, 2, 3, 4, 5, 6, 7, 8, 9. If there's 9 elements, the first one that has children has to be 9 divided by 2. Right? 9 divided by 2 is 4, right? 0, 1, 2, 3, whoops, 1, 2, 3, 4, right there, because this is at position 1. OK. If you know that, now all you need to do, OK, is downheap that element. OK, so it would go down. And what would get replaced? What would replace the 43? 12. OK, so we're going to replace the 43 with a 12. OK, and now you just walk. You continue walking back up the tree, or back going basically down. OK, so you have 43. The next one you do is 13, then 9, and then 14. Well, I don't even know if you need to do 14, right? OK, watch. Right, you check at 13, and you downheap 13. And then you check at 9, and you downheap 9. It turns out it's fine. And then you do have to downheap the roof. And you check 14, you downheap here. Now, is it quite done yet if we downheap 14 to here? Not quite. We need to actually swap it with the 11 as well, and you're done. And that actually will work every single time. So it's kind of cool. You actually split the work into 2 because you only have to downheap half the elements now, at the most. Yeah?
So if you had 10 elements to start, then you would have started at...
Yeah, if you have 10 elements, 10 divided by 2 is 5. 1, 2, 3, 4, 5. That's the first one that has children. And so you'd have to start downhipping 10, then 12, then 11, 9, 8. Kind of cool, huh? How that works out? Yeah. And that was really fast. But point is, if you go back and look at this slide right here that says insert all elements starting from the lowest possible completely filled level at the first node with children, which means the number of nodes divided by 2 works out every time. Right? Downheap each element going back up until you get to 0 and you're done. OK? Pretty simple as it turns out, and kind of cool. And the asymptotic complexity of that is actually, I don't know exactly what it is, but I believe it's log n. Yep. And then, yeah, I believe it's log n. Do that. OK, questions on heaps? Yes. You can do a binary search from the array format. The only problem, as I mentioned earlier, is if it keeps going down in one direction, every time it goes to another level, you have to double the number of elements in the array. With a sorted heap, or with a complete binary tree, which is what a heap is, you only have to double every time it gets all the way to the end here. So that's nice. Other questions? Look at Mr. standing up in class and not even ready. Any other questions on that? OK, I'll see you guys in lab or on Wednesday.